Hi. So I'll be talking about MIT's MPI-CUDA implementation of the full poisson-boltzmann equation. So in the last day, we an incrementation of that. So we've seen a growth of data. We now have the PDB, the database bank, etc. And we also have new computational architectures that weren't available when the first poisson-boltzmann solvers came around. So in that context, we wanted to port and improve the Delphi algorithm to new architectures using CUDA and MPI. So you all know this, but we'll go over it very fast. Under the approximation of continuous electric media, we have the linearized poisson-boltzmann equation. So we have our potential, the potential, fixed charges, the device length, and the dielectric constant. We want to solve that, and we use the finite difference method. After some linear algebra, which I won't bother you with because it's all been published and you surely all know it, we get to the finite difference stencil. And we use the successive over-relaxation method. So all we have to do is make this operation on every grid point. We basically take the potential on every grid point, make the sum of the neighboring points times the electric constant, and we just do the whole operation. We all the charges from the PDB file are interpolated into the cube, so no artifacts are generated. And we use modified Coulombic equations as boundary conditions, and that's it. We are basically ready to go. Nevertheless, that stencil can be improved a lot computationally. For example, there are no charges at every grid point. So taking that into account would be making several floating points operations which are not necessary. The divisor is usually you usually have two divisors. One when you are outside the molecule and one when you are inside, except on the dielectric boundaries. So you could have just a pointer with that information and not make the calculus every time. So what we did was following Delphi's algorithm. So what we did following Delphi's algorithm, it's the following. We apply Laplace rule over the whole stencil. And after we apply Laplace rule, we make a correction when charges are present and when the dielectrics change. So we make a lot less floating point operations. Even though Gauss-Seidel requires that all these operations should be done in a specific order, we can take advantage of the so-called checkerboard structure. This is important because what we want to do is parallelize the algorithm. So if we follow the order, we cannot parallelize it. Nevertheless, since we can paint the grid points with colors, and every blue grid points depends only on green points, and blue on green ones. So we can just we can parallelize the grid points with the same color. And that way we can move very fast among those two colors. First the green ones, then the blue ones. So we are all set to go. We just have to do some pre-processing to build those pointers which are going to be applied as a correction afterwards. So we have to find the electric boundaries, and we have to make a series of pointers where the charges are located to make the corrections, and then we apply the algorithm. So we first make a run on the even points or green points, and then we make a run on the blue points. That's it. So far, nothing extraordinary, and that's the standard Delphi's algorithm. So what we want to do, okay. And for the nonlinear poisson-boltzmann, what we are doing is the nonlinear term can be separated into a linear part, a nonlinear part, so that we can get close to the solution using the linear term, so that we can use the solver that we already have. And that makes it, it's useful to do that. And once we are close, the nonlinear term is added step by step, and works pretty well. Delphi works pretty well with this methodology. The nonlinear term is approximated using Taylor expansion, and it's stable. So what we want to do is take that algorithm and go fast. And there are a number of architectures and paradigms that we can use. So we basically focused on CUDA and MPI and made some tests with OpenMP. So the idea is we have a cluster. You may have a multi-core CPU, only one computer with 32 nodes, whatever, the standard multi-core computer nowadays. You may have a cluster of those. You may have a CUDA, a computer with CUDA. You may have a clusters with CUDA. You may have one node with many CUDA cards. There are many options. So what we wanted to do is somehow make an abstraction so we can take advantage of all of those situations. So it's, from the programming point of view, it's tough. You say it very fast, but you have to work hard on the machine. So let's start with CUDA. CUDA, basically, we use two-dimensional blocks. You basically can imagine the cores, each thread, it's an intersection of the lines. And those threads are organized in blocks. Each block has a shared memory, so each thread can get the value of the points around with no extra penalty. As we saw on the stencil, what we're doing is basically taking the points around us and then making corrections. So we can do that very fast, but on the threads which are close to the border, we can't because there is no shared memory between the blocks. So we have to make data, we have to access the global memory to do that. What we did, the way the software was done was use a linear index. So we didn't use a 3D pointer. We use a 1D pointer because it's much faster to go along one dimension. And the relationship between the threads and the index in the cube, it's given by the standard 3D to 1D index relationship. Only that, in this case, we don't only move from a 3D to a 1D index, but we're moving on a even odd kind of way. So it's tricky. Nevertheless, we can see that also in each block, it's surrounded by green points. So we basically have the same structure. So the neighboring points are already in shared memory. We don't have, once the potential is passed to the GPU, the way we're moving is in the theta direction. So we can imagine each slice being allocated in the shared memory. Then the potential up and down have to be fetched from global memory, and to eliminate the number of fetches to global memory, each call to the top part then is used as the bottom for the next iteration. So we saved one call to the global memory. Charge and electric constants were loaded as textures, and so basically that's the algorithm, in a very succinct way. And these are the results we got with the GPU, one single GPU. We got a speed up of about 10, which is not great. I mean, sometimes you heard people working with GPU and they get 180% speed up. With poisson-boltzmann, it's not that easy to get those numbers, because the issue is the memory access. I mean, each thread is not independent. So you have to have a lot of communication between the threads, and that on the GPU, it's a huge penalty. We got about the same speed up for the linear and non-linear equation, all were done fully on the GPU. And for example, the NVIDIA test bandwidth on the Tesla card what we used gave around 70% of the theoretical bandwidth. We achieved 40%, which is not bad. I mean, because the card using the NVIDIA bandwidth test that is only passing data, you get about 70. But we are not only passing data, we are making calculations, etc. So I think it was pretty well done, the algorithm. So next, we have MPI. So MPI is a message passing interface. It's a standard. There are different implementations, and it allows for a deeper control of the parallel execution. It's much simpler than GPU. To program in CUDA, I mean, you have to take the data to the card, etc. With MPI, it's simpler, and you work on the CPU, and you have asynchronous or synchronous communication, and we'll talk about it later. And it's made mostly for distributed memory systems. So you have a cluster, different CPUs. Nevertheless, it can be used with only one CPU. Great. So we made a test with poisson-boltzmann between MPI OpenMP, which was, I mean, I really wanted to see how it went. And MPI beat OpenMP by far. I mean, you'll see results with MPI, and for a shared memory system, you'll expect OpenMP to be at least close as good, but we didn't get very good results. So what we did with MPI was, you can imagine your molecule inside a volume, and we cut the volume along the theta axis. So what some people have done is, since you're working on a one-dimensional pointer, you take the one-dimensional pointer and you divide it on n pieces, and you work on that. Nevertheless, since what we wanted to do was to try different, I mean, from a software engineering perspective, use different paradigms, CUDA, MPI, etc., together. We wanted to have each parallelization paradigm to work alone by itself. So that way, in each little cube has boundary conditions. I mean, it's a solver on its own. You can treat it as is, you have a molecule inside in each one, and doesn't depend on the other cubes. All you have to do is the message passing between the upper and lower faces of the cube, which you need because you're taking all the points around. So the message passing has to be blocked, because if you're doing first the red points, then the green points, in that order, you need the green points information to do the next ones. So you have to wait for the message passing. Data has to be transferred after each color is updated in each of the boxes. And so that's all the extra code that had to be added, and a collect called to get the error after each solver, independent solver, was done. And these are the results. I didn't want to bother with going to much of the detail of the MPI implementation, because it's really you're probably not interested. But the results we got are pretty nice. This is for the linear equation. So the first thing that I want to say is that these are preliminary results. Ideally, what you would do is make many runs, take statistics to avoid noise, because this server is in production, people were running things. So for example, at the end, we have a little increment on the MPI communication time. Maybe somebody was using it, there was more communication, but nevertheless, the results were fine. So this is a work in progress. So the time decreases nicely, and we had a linear speed up, okay? With the linear and non-linear. And that's nice because, previously what we had seen was people achieving a speed up close to linear or linear on the non-linear poisson-boltzmann equation, but not so much speed up using the linear poisson-boltzmann equation. So we got a good speed up on both. The slope, it's about a half, so it could go faster, but as preliminary results, we are heading in the right direction. So then, okay, you have MPI. You can work on many cores. So the next question is, okay, since we isolated it, you could have now a cluster of GPUs. You could have one GPU or many GPUs on one node. So using the same software, the nice thing about the software that we are working on is that it's the same one for every case. So somebody takes it, compiles it with Gmake, and it's the same one. So you have two levels of abstraction on the parallelism. And with 4 cards, we got close to 3 speed up. So if you have 3 cards, you could go 30 times as faster as one CPU. That's very nice. We haven't tested many GPUs on many nodes, because basically the node we have doesn't have InfiniBand. And so the tests we made, basically as soon as you started using another node, there was no gain, because the communication is essential. So we saw a drastic change between using Ethernet and InfiniBand. That's not always the case. There are many simulations which you may run perfectly without InfiniBand, but poisson-boltzmann, it's not one of them. We lived it. So next steps. So this is a work in progress. So what we're trying to do now is to break the synchronous communication. So the issue is that we have many nodes doing first blue, red, the nodes, the color of each node, and they have to be message passing between them. So what if we manage so that the nodes, alternating nodes, do different color? So that way we can do the message passing while the GPU or CPU or whatever is working. So we have non-blocking communication, and we can put that slope closer to 1, which is the ideal. It's a little bit tricky because even though, I mean, you say you only switch, make, instead of the one, you make the next one, that's it. The green color still needs the previous data, so we have to sit and code a little and make it work, but we are very confident that pretty soon we'll get it. Also, we noticed that the cache usage can be optimized. I mean, when we were starting and playing with the MPI implementation, with the small molecules, we got a speed up above linear, which makes no sense. I mean, the top is linear with a slope 1. So what is happening is that since you have a smaller cube, each process is working on a smaller cube, it's using better the cache memory. So what we want to do is optimize the cache so that we can go even faster. So maybe, hopefully we won't go 30 times faster with 4 GPUs, but I don't know, 50, hopefully. I don't know. So then also improve the nonlinear parallelism, because, I mean, you would expect that the nonlinear equation should be parallelized better than the linear one, because you're making more number crunching. So we have to improve that. Last remark, we already have, if you use Delphi, we have a GPI and an OpenMP model that will be putting online soon, so that you can update the solver of you can update the solver so that with Delphi 77 you can already use the GPU and get a 10 times speed up. And it's very easy to install. We'll put all the info when it's on the electrostatic zone page, and you're welcome to use it. Thanks.